Again, as I said before, the W is the input prices, which can be W1 or just simply W for the case of labor, which can be R as the case of capital. And the P is the output prices. Output prices. It can be P1 for the output one. It can be PL minus H for the output L minus H. But in the case of only one output, then we have only one P. Because we are producing one output and we are selling just one output to the market. But mostly, in order to make it simple for the profit maximization, we consider only one output. Because when we have one output, so easily we can have one function. So this is one output, but two input. When we have different outputs, so it will be so complicated to maximize our profit. That's why we mostly assume that the firm produces only one output. Only one output, profit maximization. In the case of only one output, then this P is the price of our output. And again, this W is the price of inputs, and this X is our input. So then, when we have this kind of profit maximization problem, how we can maximize our profit? We have this one, which is our pi. Our profit is equal to P multiplied by f of X minus Wx. Or if we have, like, let's make it more, f of X minus WL, sorry. For example, we have two input, W1x1 minus W2x2. This is our profit function. How we can maximize this profit function? By using partial derivative. But here, we don't need Lagrangian because we don't have constraint. In case of utility maximization, we were needed Lagrangian because we had a constraint that was budget constraint. But we have, although we have constraint that we are going to maximize our profit by using some level of output, but that output itself is included in our profit function. Fx is also already there. So that's why we are taking the partial derivative. The partial derivative of pi with respect to, for example, first time with respect to x1, and set it equal to 0, then the partial derivative of profit with respect to x2, then set it equal to 0. When we take the partial derivative of pi with respect to x1, then with the partial derivative of pi with respect to x2, we will have two equation and two unknown. When we have two equation and two unknown, it's easy to solve. For example, here, let's suppose that our f of x, which is x1 and also x2, is equal to this Cobb-Douglas production function. So then our pi is equal to P multiplied by x1 to the power of alpha, x2 to the power of 1 minus alpha, minus W1 x1 minus W2 x2. So now first let's take the partial derivative of this profit function with respect to x1, which will be equal to P alpha multiplied by P x1 to the power of alpha minus 1 multiplied by x2 to the power of 1 minus alpha. Then minus. Then the partial derivative of this term with respect to x1, we will have only w1, and it's equal to 0. Is equal to 0. And then the partial derivative of pi with respect to x2, then in this time, 1 minus alpha multiplied by p multiplied by x1 to the power of alpha, x2 to the power of 1 minus alpha minus 1, then we will have only minus alpha. Minus, then the partial derivative of this one with respect to x2 is 0, then the partial derivative of this term with respect to x2 is equal to w2. w2 is equal to 0. So now we have two equations, equation number 1 and equation number 2. We have two equations and two unknown. Where our unknown variable here is x1 and x2, which is our input. We need to set up the optimal level of input that produce the maximum output that maximize our profit function. So we can further, do I have some space here? Also, in the first equation, if we move w1 to this side and also w2 to this side, it will change to this equation, which is alpha px1 to the power of alpha minus 1 x2 to the power of 1 minus alpha equal to w1. Because w1 now moving to another side of the equation. And here, is equal to w2. Is equal to w2, w1, w2. And so now, if we divide this one, which was our equation 1, and this one, which was equation 2, if we divide equation 1 over equation 2, then we will have w1 divided by w2 is equal to this term, or alpha p x1 to the power of alpha minus 1 x2 to the power of 1 minus alpha, and this one 1 minus alpha p x1 to the power of alpha x2 to the power of 1 minus alpha. Or in a general way, if we take the partial derivative of our revenue was p multiplied by y. Yeah? If we take the partial derivative of revenue with respect to x1, what will we get? We will get the marginal product of x1. And if we get the partial derivative of that one with respect to x2, we will get the marginal product of x2. So then this one is marginal product of x1. This is marginal product of x2. And we know that the marginal product of x1 divided by the marginal product of x2 is the marginal rate of technical substitution. It should be equal to the price ratio. If you remember, we had the similar condition for the case of utility maximization. In the case of utility maximization, we had the marginal rate of substitution should be equal to the price ratio. There was P1 over P2, but here, because we are talking about input, it's W1 over W2. So for the profit maximization, when we have this condition, we can maximize our profit. And also another simple way is that For example, from 1, because now we have 2 unknown and 2 equations, one of the way that we can solve to find out the optimal level of x1 and x2, for example, from the first equation, find out x1 in terms of x2. I mean, keep the x1 in one side of the function, move all other terms to the other side of the function, to this equation. Then substitute the value to this one. For example, here can be x1 to the power of 1 minus alpha is equal to w divided by alpha p x2 to the power of 1 minus alpha. This one. Keep this one in what side of the equation? Move the other to the other side of the equation. So in that case, we have to divide both sides of the equation to alpha p x2 to the power of 1 minus alpha. x2 to the power of 1 minus alpha. You can also write down as this one. W divided by alpha p multiplied by x2 to the power of alpha minus 1. So now, so we have alpha minus 1 here, we have alpha minus 1 here. So what we can do, we can raise up both sides of the terms by this one, 1 divided by 1 minus alpha. So this one will cancel out with this one will cancel out with this one, then we will have x1 as this one. W over alpha p to the power of 1 divided by alpha minus 1 x2. Then the value of x1, the value of x1 in terms of x2 is this one. Now as you can see, x1 is a function of x2. And instead of x1, in your second equation, here we have x1. Just substitute this one to this value. And when we substitute that one to this one to that value, then in this equation only we will have x2. Only we will have x2, and also we will have w2, p, and w1. And finally, what we will get x1 as a function of p, which is the output price, as a function of w1, which is the price of first input, and the function of w2, which is the price of the second input. So then we will have this kind of Beaumont function for our input. At the same time, for the x2, also we will have some function of p1, w1, and w2. So this is the optimal level of input Beaumont with respect to the output price and input prices to maximize our utility. To maximize our utility. Then we can substitute the value of x1 and x2 to this production function. x1 to the power of alpha, x2 to the power of 1 minus alpha. Then what we will receive, we will get some value like this, which is our supply function. Which is our supply function.